So till now we have seen the theoretical development of equations to determine the friction factor, heat transfer coefficient, entrance length, both hydrodynamic entrance length, thermal boundary entrance length, and then hydraulic mean diameter calculations, etc. Now let us quickly have a look at different types of problems. Air enters at a temperature of 60 degrees and flows through 2.5 centimeter dia tube with a velocity of 0.8 meters per second. It can be heated either by condensing steam on its outer surface or by electrical resistance heating. Calculate H in both the cases. Assume fully developed flow. So the properties are extracted, and condensing steam on its outer surface, it may be at atmospheric pressure, it is 100 degrees centigrade. So therefore the properties are estimated at that. The temperature remains constant, so that problem belongs to constant surface temperature. And by electrical resistance heating, it is a constant heat flux case. First Reynolds number is calculated, Vd by nu 963 less than 2300, hence it is laminar. Condensing steam means maintaining constant wall temperature. Electrical heating means maintaining constant wall heat flux. In constant wall temperature for laminar flow, Nusselt number is 3.66 fixed, which is equal to Hd by K. So therefore H is equal to 4.39 over. And in constant heat flux laminar, Nusselt number is 4.66, which is again equal to Hd by K. So therefore H equal to 5.23. See, that is the advantage we have in laminar flow. Directly we take the Nusselt number from the tables for circular pipes under laminar condition, and then we calculate the value of H. Another problem. Water flows through a 25 mm dia pipe at the rate of 5 kg per minute, entering at 20 and leaving at 70. Again, electrical heating is done at the rate of 10 square kilowatt per meter square. Calculate the length of the tube required and convective heat transfer coefficient. Very important application oriented problem. So, this is a constant heat flux problem, internal flow because water is flowing through the pipe, forced convection of course. It enters at 20 and leaves at 70. So the bulk mean temperature is 20 plus 70 by 2, that is 45 degrees centigrade. So properties we have to estimate at 45 degrees centigrade. And the heat flux is given as 100 kilowatt per meter square area. So total heat supplied is heat flux into area, that is 10 square into pi dl surface area, which is nothing but equal to mCp into delta T, 70 minus 20. So that will give you the length of the pipe 2.22 meters. Finish. Easiest way. So 10 square into pi dl is mCp T alpha 2 minus T alpha 1. So you will get 2.22 meters. Now to determine the convective heat transfer coefficient, let us take the bulk fluid temperature as 20 plus 70 by 2, 45, and calculate, extract the properties from the data book for the water at 45 degrees centigrade, and then calculate Reynolds number, Vd by nu or 4m by pi d mu, because m is given 5 by 60 since it is given in kg per minute. You will get the Reynolds number. 7118 means it is turbulent flow. So for turbulent flow, let us use the Datus-Boiler correlation. Nusselt number is 0.023, Re to the power 0.8, Prandtl number to the power 0.4. Why 0.4? Because while water is passing through the tube, it is getting heated up. So you will get the value of Nusselt number 48, which is equal to Hd by K. You know the K value and you know the diameter of the pipe. You will get H value 1219 watt per meter square Kelvin. So So that is how you have to determine the convective transfer coefficient and length of the tube required. Another problem. Water at 60 degrees enters at 2.5 centimeter velocity and is heated keeping wall temperature constant at 100 degrees by condensing steam. Take the length of the pipe as 6 meters and find the exit temperature of water. Assume the flow is fully developed. Now again, water enters at 60 degrees. We don't know what temperature it is leaving, but the surface temperature is maintained constant at 100 degrees centigrade. So therefore, what we will do is, to assess the Reynolds number, we need to have the properties of water at bulk mean temperature. Bulk mean temperature is inlet temperature plus exit temperature by 2. Since we don't know the exit temperature, we assume that the property is at 60 itself, and then we will proceed. Based on the final answer we obtain, we will go for iteration procedure and then find out whether in the second run or third run the estimated assumed values will coincide with the practical ones or not. So let us start with properties at 60 degrees. These are the properties extracted from the data book for water, and now calculate Reynolds number 1053. So it is laminar. For constant wall temperature, Nusselt number is 3.66. So calculate H value, 95.26 watts per meter square Kelvin. Now M is equal to rho A into velocity. Rho we know, area we know, pi by 4d square. Velocity is given as 2 centimeters per second. You will get the mass flow rate. And the Q is equal to HA, H into surface area, pi dl, Ts minus bulk mean temperature, T alpha 1 plus T alpha 2 by 2 equal to MCP T alpha 2 minus T alpha 1. We know everything except T alpha 2. H is already found, pi dl is known, Ts is known, T alpha 1 is known. So by supplying the values, determine the value of T alpha 2. So the T alpha 2 is 88.57. But we have assumed the temperature as 60. So 60 plus 60 by 2 is 60. At what temperature we have taken? Now we got T alpha to 88.7. So the bulk mean temperature becomes 60 plus roughly 89.2, 74.5, whereas we have taken the properties at 60. So our assumption of 60 is wrong. So now let us assume the bulk mean temperature as 60 plus this new temperature divided by 2, 74. Take the properties of 74.5. Reynolds number is again less than 2300. Laminar, Nusselt number is 3.66. Same thing, H is 97.10. Q equal to HA Ts minus same equation. You will get now T alpha 2 is equal to 88.9. Same 88.57, 88. So there is not much error between 88.57 and 88.9. So we can take it into grant. Another problem. Consider the flow of oil at 10 degrees in a 40 centimeter pipeline at an average velocity of 0.5 meter per second. Length of the pipe is 300 meters, subjected to icy waters at 0 degrees centigrade. The surface temperature of the pipe is nearly 0. So determine the temperature of oil when the pipe leaves the lake, oil when it leaves the pipe, the rate of heat transfer from the oil, and the pumping power required to overcome the pressure loss. This is the figure you can assume. It enters at 10. What is the leaving temperature? 0 degrees, etc. So the assumptions are steady operating condition, hydrodynamically developed. Again, in this case also, we don't know the exit temperature. So as a first step, we assume the properties at inlet temperature, that is at 10 degrees centigrade. So initial approximation, we evaluate the properties of oil at 10 degrees. If the final answer does not coincide with this 10, we will repeat the calculations thinking that the assumed value is wrong. So these are the properties extracted for the oil at 10 degrees centigrade, and surface area of the pipe is pi dl, mass flow rate through the pipe is rho area of cross section into velocity, and hence you can find out the Reynolds number Vmdh by nu 77 laminar flow. Thermal entrance length is 0.05 Reynolds number Prandtl number into d, roughly 44,275 meters. But anyhow, we assume that it is thermally developing flow, and we take the equation for, see, the pipe length is only 300 meters, whereas thermal entrance length is 44,275. You can't treat it as a fully developed flow, so we treat it as a thermally developing flow, for which the equation proposed is 3.66 plus etc. etc. Substituting, you will get 24.44, from which H value is 8.92 watt per meter square degree centigrade. And now once you know the value of H, you can determine the exit temperature of water. Assuming that it is exponentially varies, you can say Ts, a logarithmic relation or exponential variation. You can calculate the temperature TE equal Ts minus of Ts minus Ta e to the power minus HAS by MCP, 9.68 degrees centigrade. Actually, we have assumed it as 10. We got the answer as 9.68. The drop is only 0.32 degrees. So therefore, there is no need to again rework the problem. Approximately it remains the same. And the exponential variation we have assumed. So therefore, logarithmic mean temperature, which we will come to know in the chapter on heat exchangers, Ti minus Te by logarithm of Ts minus Te by Ts minus Ti is coming around 9.84 degrees centigrade, and Q equal to H into surface area into logarithmic mean temperature equal to minus 3.3 into 10 power 4. So therefore, this much amount of heat it will lose, the oil, and logarithmic temperature difference is identically equal to arithmetic mean temperature difference between, because delta Ti is equal to delta Te, both are same. The laminar flow of oil is hydrodynamically developed. That is now to determine the pumping power required for it. So let us find the friction factor. It is laminar, so F is equal to 64 by Re. Now pressure drop is FL rho V square by 2D, 69.63 kilopascals. And now pumping work required is m dot into delta P by rho, or mgh, same equation. Delta H, this is the, in the place of H you have delta P by rho, which is equal to 4.4 kilowatts. So thus 4.4 kilowatts work is required to pump the oil in a 300 meter long pipe through the lake to overcome that friction. Now one more problem. Consider water at 15 degrees centigrade flowing in a 4 centimeter dia 30 meter long horizontal pipe made of stainless steel steadily at the rate of 5 liters per second. Determine the pressure drop and pumping power requirement to overcome this pressure drop. No heat transfer calculation, pumping power and requirement to overcome the pressure drop. So this is the figure. Water is flowing through this pipe. The properties are at 15 degrees centigrade, rho value, mu value, and the flow rate is 5 liters per second. So therefore, velocity of the fluid flow is divided by cross sectional area, 3.98. rho Vd by mu, which is greater than 2300, hence the flow is turbulent. And for turbulent flow, pipe roughness is given. It is a stainless steel. So therefore, assuming 0.002 in 10 power minus 3 as the roughness parameter by d, for which we use the equation 1 by root f minus 2 log epsilon by d 3.7 etc. You will get f is equal to 0.0171. Once you know f value, pressure drop due to friction is FL rho v square by 2d, so many kilopascals. Therefore, pump work is equal to discharge into pressure drop, which is equal to 508 kilowatts. See, because it is not a smooth pipe, we have gone for epsilon by d, etc. If you assume it as a smooth pipe for turbulent, you can use the other relation and calculate the power requirement. That power requirement will be much less than 508 watts. Another important problem. Water is to be heated from 10 to 80 in a 2 centimeter internal diameter, 7 meter long tube. The tube is equipped with an electrical resistance heater, so it is a constant heat flux problem. Outer surface of the heater is well insulated, so steady state operation. So water flow rate is 8 liters per minute. Determine the power rating of the resistance heater. How much is capital Q? Or also estimate the inner surface temperature of the pipe at the exit. Very interesting. Heat flux problem. Figure is like this. Enters at 10 and leaves at 80. So bulk fluid temperature is 10 plus 80 by 2. Heat flux is something like this. So wall temperature also increases. Okay. Now bulk fluid temperature is 10 plus 80 by 2, 45. Take the properties at bulk mean temperature, and cross sectional area of the flow is pi by 4 d square, and the surface area of the pipe is pi dl, and mass flow rate is density into discharge. You will get 0.132 kg per second, and the rate of heat transfer is mass of the fluid specific heat into exit temperature minus inlet temperature, 38.63 kilowatts. So all this energy must come from the resistance heater, therefore power rating of the heater must be 38.63. You can also determine heat flux Qs using the formula H into Ts minus Tm, where Tm is the bulk mean temperature. So Ts is Tm plus Qs by H. And Qs is total heat divided by the surface area through which the heat is entering. So it is 87.83 kilowatt per meter square. And the average velocity Vm is discharged by cross sectional area, roughly 0.424 meters per second. And now, knowing this average velocity, you can determine the Reynolds number, 14,100. So the flow is turbulent. If you calculate in the turbulent region, if you calculate the hydrodynamic boundary length, hydrodynamic entrance length or thermal entrance length, it is around 10 times diameter, 0.2 meters. So when compared to the pipe length, this 0.2 meters is too short, so let us neglect and assume that the flow is fully developed in the entire pipe. And Nusselt number is calculated using the Dittus boiler correlation, 0.023 or Reynolds number to the power 0.8, Prandtl number to the 0.4, 82.78. That will give you the H value 2636.8. Now once you know H value using this equation, Q dot S is HTS minus Tm, or Ts equal to T average plus Q dot by H. T average is 80. You will get the value of Ts as 113 degrees centigrade. So this is a problem on heat flux turbulent condition. Now let us see a non-circular cross-sectional pipe, a duct. Air conditioning section system duct of 40 by 80 centimeters square area through which air is flowing at 20 degrees centigrade with a velocity of 7 meters per second. You have to estimate the heat loss per meter length. So hydraulic mean diameter, properties are given like this. Hydraulic mean diameter is 2AB by A plus B, that is 53.3 centimeters. Now Reynolds number is calculated based on the hydraulic mean diameter, which is 0.248 into 10 power 6 turbulent flow. And Prandtl number is mu Cp by K, which is 0.7. And Nusselt number, because it is Just only few minutes, 2 or 3 minutes I will give. I will continue with problem number 7. Mr.
Yes.
Sridhar?
Yes.
Can you hear me?
Yes.
I will continue with problem number 7 so that you can attach from there.
Okay.
Just few minutes on the last problem. So let us move to the, shall I start?
Yes, sir.
Okay. So let us move to the problem number 7, wherein an air conditioning system is taken in which air is flowing through a rectangular duct. So far we have seen the problems related to circular cross-sectional pipes. Now let us take a rectangular duct of 40 by 80 centimeters through which air at 20 degrees centigrade is flowing with a velocity of 7 meters per second. You are asked to determine the heat loss per meter length and per unit temperature difference. Properties of air are also given, so you need not worry about the bulk mean temperature, etc. So because the cross section is not a circular one, we have to calculate the hydraulic mean diameter. DH is equal to AB by A plus B, where AB dimensions are 80 centimeter, 40 centimeters. You will get the mean diameter as 53.3 centimeters. Corresponding Reynolds number is 0.248 into 10 power 6. So this is quite big and the flow is turbulent. Only properties K, nu and alpha are given. So by using these properties, the Prandtl number is momentum diffusivity to thermal diffusivity ratio, nu by alpha. You can calculate it as 0.703. Since it is turbulent flow, let us revoke Dittus-Boylt correlation. Nusselt number equal to 0.023, Reynolds number to the power 0.8, Prandtl number to the power 0.4. It is a heating application, so we are using 0.4 here. The air flowing through the air conditioning duct will absorb heat from the surroundings, so it gets heated up. So the index N is used here as 0.4. So when we substitute the Reynolds number and Prandtl number, we will get Nusselt number as 414.2, which is nothing but H into hydraulic mean diameter by K. From this we can determine the value of H. It comes around 20.13 watt per meter square Kelvin. Now to determine the heat loss per meter length, let us first calculate the surface area of the duct per meter length. Surface area formula is perimeter into length. Perimeter of the duct is 2 times A plus B into L. It is 2.4 meters square. And now Q is HEAS delta T. Since you are asked to determine per unit temperature difference, we will take delta T as 1 and it comes around 48.3 watts. So this is how we have to solve the problems in internal flow for different cross-sectional flow arrangements. We have seen laminar and turbulent, constant wall temperature, constant heat flux, and one cross-sectional area other than that of circular. Now what is that we have covered? Reynolds number is defined as rho Vd by mu or 4m by pi d mu. In case of non-cross-sectional areas, in the place of d we have to use hydraulic mean diameter given by 4 times cross-sectional area by perimeter. While calculating the Reynolds number or Prandtl number, the fluid properties are to be considered at bulk mean temperature, which is nothing but inlet temperature plus outlet temperature divided by 2. If we don't know the outlet temperature, we have to assume some value and then we have to proceed. Finally, we have to calculate the outlet temperature, and if the assumed value and the calculated one are same, it is okay. Otherwise, we have to go for iteration by assuming another value which we have obtained in the first case as the one which obtained in the first case. In case of laminar flow, when the temperature of this surface is maintained constant, Nusselt number is given by 3.66, and in case of constant heat flux, the Nusselt number is 4.3. The Nusselt number is considered as 4.36. And for turbulent flow inside the tubes, the famous correlation, Littus-Boyleter correlation is used. Nusselt number is 0.023.